Hi everyone, I'm Nikhil Garg, and I'm really excited and humbled to be here to talk about my dissertation work. This, of course, wouldn't have been possible without my advisors Ashish Goyal and Ramesh Johari, and all my co-authors. My dissertation work has mostly been about problems at the interaction between computer science, operations, and society, and in particular about the platforms that increasingly permeate our lives. These platforms help us find transportation or work in two-sided marketplaces. In an application that might be less familiar, they also help us make decisions in groups in unstructured ways. Here, think of standard voting, but in far more complicated spaces, like how a city can vote and how to allocate a few $1 million across many projects. When designed well, these platforms have the power to make a large positive difference in many people's lives by allowing connections that otherwise would not be possible. But of course, the opposite is also true. And that's why it's really important to design these things well. What do I mean by design? The platform has to make certain decisions to support interactions. In two-sided marketplaces, they have to match two sides, or recommend people as matches, or price those matches. On civic engagement platforms, they have to find ways for people to share their opinions quickly and without too much cognitive load. And then they need to aggregate those decisions into things that well represent the group. In practice, these decisions are made by a combination of methods, both theoretical and empirical. This often leads to a really nice division of labor, but it's often hard to make these methods play well together. What's an essential feature in much of my work is the interaction between methods, to try to go end to end by connecting implementable design decisions to the behavior that it might induce, and in turn an objective that the platform might care about. So what I'm going to do in the rest of this talk is I'm going to briefly give you an overview of the dissertation structure right now. And then I'm going to try to be a bit ambitious and give a quick illustration of one chapter in each part of my dissertation. Part one is on pricing on online marketplaces. In particular, I'm going to be thinking about how to design surge pricing on ride-hailing marketplaces. And this is with Hamid Nazarzadeh. Part two is about how to design rating systems on online marketplaces. And this is composed of two works with my advisor, Ramesh Johari. Finally, part three is about how to design voting systems on civic engagement platforms. And these two are joint work with my advisor, Ashish Goyal, and many other people that I'll list later. And a running theme that I'm going to try to keep coming back to is how to interface between theoretical and data-driven approaches in order to answer practical design questions for real systems that exist. Okay, so let's get started. Price one is on a paper called Driver Surge Pricing. This is joint work with Hamid Nazarzadeh and started when I was an intern at Uber's driver pricing team in the summer of 2018. A core fact of ride-hailing marketplaces, much more than any other marketplace I've seen, is that demand fluctuates quite substantially with time, both on the order of days and on the order of minutes. So for example, on these plots from public data from the Ride Austin marketplace, we can see that there's quite predictable patterns on the order of a week, with weekends being far more busy than the rest of the time. But then we see that demand fluctuations on the order of minutes is quite stochastic and also highly variable. This fast demand fluctuation has important implications for how the platform should be designed. And in my view, this is a highly understudied topic in the area. In this paper, we focus on the impact of this demand fluctuation on drivers, and in particular, how platforms should pay drivers. To motivate why this might be important, I'll show you part of our empirical finding. In this plot, the vertical axis is a measure of how much a given trip request increases a driver's long-run earnings. I won't have time here, but I'm happy to describe how it's measured offline. The horizontal axis is what's called the surge factor, which is a proxy for how expensive the trip is and how much the driver is being paid for that particular trip. What you might expect to see is an increasing line, is that as how much the driver is being paid for that trip increases, the increase in the driver's long-run earnings increase. And what we rather see is that story is only half true, in that for certain types of trips longer than the median trip length here, for example, that is true. in that the more the driver is being paid for the trip, the more their earnings actually increase in the long run. But for short trips, that's actually not true. In the summer of 2018, I was a part of the driver pricing team at Uber, where the team had noticed a similar pattern there. And so we were in the process of changing of how search functions. The historical standard of search pricing, even for drivers, was what's called multiplicative search. Whatever the base value of a trip, that gets multiplied up during search. And so, for example, if the search factor is currently a 2, then a $10 trip becomes a $20 trip, and what's normally a $30 trip would become a $60 trip. Under the new additive search system, rather a fixed value gets added to each trip. So during a $15 surge, a trip that regularly costs $10 would now cost $25, and a $30 trip becomes $45. This might seem like a small algebraic change, but it took a large team over a year to implement and deploy. And so in this work, I want to think about this change in a more principled manner and to try to answer, was this change even a good idea? And why? And in what cases is this a good idea? Is it always a good idea? Is there an optimal mechanism that maybe generalizes this change that would work in all parameter regimes in all settings? And hopefully these questions will try to get at what other marketplaces should think about adopting such changes. What we end up finding theoretically is the following. First, the old pricing model of multiplicative pricing functions really well in a world without demand dynamics. In such a world, it would value trips correctly. However, in even a simple model in which demand fluctuates over time stochastically, it no longer works. Trips are misvalued, and drivers have an incentive to accept or reject some trips over others. Finally, we develop a pricing scheme that correctly values trips even with such demand dynamics. However, going back to this theme I had at the beginning of trying to do implementable mechanisms, something as complicated as the algebraic form I have here might not be practical for a variety of reasons. And so we really want to see whether a multiplicative or additive approximation of this scheme is best. We do some comparative statics in the paper, but really you should turn to data in order to answer this question about real-world approximations. And so what we end up finding is, of course, the plot that I showed you earlier is that a multiplicative surge pricing incorrectly values trips, and in particular values long surge trips over short surge trips. On the other hand, additive search does approximate this scheme quite well in the parameter regimes that matter for ride hailing, and so values trips correctly. And so while the optimal scheme might not be practical, we did find a good enough scheme for practice, and that can be shown to theoretically align with the optimal scheme in common parameter regimes. That is all I want to say about this work, but I'm happy to answer questions offline. In part 2 of my dissertation, I think about how to design rating systems on online marketplaces. And I'm going to talk about the first paper here, Designing Informative Rating Systems, Evidence from an Online Labor Market. This is joint work with Ramesh Johari. After an experience on an online platform, you're invariably shown something like this, so that the platform can learn from your experience. The resulting ratings are then used to make platform access and recommendation decisions. And so how to think about rating systems is really about the information content they provide. Unfortunately, a lot of the literature has shown that rating systems are uninformative in practice. In particular, when star rating systems are used, most people are giving 5 stars most of the time. And so nothing distinguishes a low quality experience from a high quality one. This has been observed across many platforms. In this part, we try to overcome this rating inflation problem. At a high level, we show how platforms can design the information that they obtain from people. The first component of this overall framework is an experimental empirical design component in which the visual design of the platform affects the information that it is received. In this case, we run an experiment on a large online labor market in which the rating question asked of raters affects the distribution of answer choices. So something like, is this the best freelancer you've hired, yields far different rating distributions than does, rate this freelancer from 1 to 5 stars. And we find that this is exactly true. On our experiment over several months on a large online labor market, we do see quite substantial distribution shifts from scales designed to reduce rating inflation, exactly in the way that you would expect. In the second part of this framework, we then theoretically think about how the information that a platform receives affects its objective. In this work, that translates to the question of how does the rating distribution of a platform affect how quickly the platform learns about participants. By which I mean, let's say that the platform cares about recovering relative seller quality. It turns out that the large deviations rate at which it can do so depends on the rating distribution in a way that can be calculated. Thus, you can compare different designs by the distributions that they induce, which induces a metric on how quickly the platform learns about sellers. We can then use this framework to answer questions like, let's say I've run an A/B test, like in our large online labor market. With all these different rating systems, which one should I use and deploy? We can also answer things like, are there contexts where inflated rating systems are good? Or more generally, what are the properties of an optimal design? Lastly, in part 3, in a chapter that I'm not going to discuss in this talk, we also we extend this framework to think about how to design voting systems. To sum up this part, I want to go back to the running theme I had at the beginning. In order to design a good rating system for a platform, you really need to go end to end. First, with the human-computer interaction component, thinking about how the design of a platform affects the information that you receive, how people behave on that platform. And then a theoretical component to reason about how the information that you receive affects the platform objective. Finally, we're going to change gears a little bit and think about designing voting systems. I'm going to focus on the first paper in this talk on voting in continuous basis. But as you'll see, many of the themes of the previous sections will also apply here. Many of the joint decisions we want to make as a society are complicated. For example, lie in high-dimensional continuous spaces. Our voting methods, on the other hand, are often not built for such complicated decisions, and so lead to many challenges. If you've ever voted for referendums in California, you know exactly what I'm talking about. The specific context I want to think about in this talk is participatory budgeting. Our research group has a platform that has been used in over 75 elections, allocating tens of millions of dollars with tens of thousands of voters. Today, I'm going to give you a brief preview of a chapter in my dissertation that is a bit more conceptual and not a mechanism that we've actually deployed in these real elections. But some of the other work in this dissertation does have practical implications for these elections where people vote on how to spend a set of money. In this work, we want to devise a mechanism to vote in high-dimensional continuous spaces. The challenge here is that voters may not be able to articulate their preferred overall budget or have the patience to do so over many dimensions. However, voters might be able to tell you what they like or dislike about a proposed budget and to make small local changes. If voters are then modeled as coming sequentially, you get a mechanism that starts looking like gradient descent. And it turns out if you set up the correction correctly, we show in this work that in many settings you actually do get theoretical guarantees of convergence through a reduction to stochastic gradient descent. Okay, so an idea where each voter is making local changes to a proposed budget works in theory, but does it work in practice? Of course, voters might be confused with the mechanism or otherwise not behave as a model based on utility maximizing rational agents suggests they should. To answer this question, we built an intuitive interface and ran budgetary elections on the US federal budget on Amazon Mechanical Turk. Each person comes in and can use the sliders as shown in order to make changes in a local ball. And we find that the mechanism across a variety of settings does indeed converge in practice across many runs, even as people do not behave exactly as the theory predicts. And so we again find in this work that this mixture of methods between theory and then just building and running something allows us to validate a proposed mechanism. So with that, I'm going to wrap up by emphasizing 2 points that this work has taught me that I hope to take forward. First, I believe that market design and operations techniques can continue to speak to large societal challenges. To solve real problems, you often need to go deep into practice and an application area, and maybe even build things or work with those who do. Second, there are many interesting research questions at the interface between techniques, and negotiating how to apply together tools from different fields is an often fruitful area of research. And with that, I'm just going to briefly flash a slide. This, of course, dissertation couldn't have been done with a million people helping me out through these last 5 years. Most chiefly, of course, my advisors, Ashish Goyal and Ramesh Shahari. Thank you. Bye.